The last talk of the afternoon session is by Jesús González from CINVESTAV, who will talk on topological complexity and generalized Hopf invariants.
Thank you very much. And thank you very much for the introduction. Very nice. Okay. Yeah, that's I want to give some ideas, some homotopic ideas about this model that was introduced at the beginning of this century by Michael Farber, to give a model to study the motion planning problem in robotics from a topology viewpoint. So here is the plain definition. The definition is very, very simple. Suppose you have space X, and you take the space of free paths on X. Then you have this vibration from the space of free paths down to X times X that sends a path into its value at 0 and 1. This is just the endpoints evaluation vibration. And then you can take the sectional category of that vibration, and that's defined to be the topological complexity of your space X. Now let me just recall for you what the sectional category of a map is. What you're looking at is taking the minimal number of open sets covering the base space, so that the vibration admits a section on each of these sets. Now, a few remarks. This is supposed to be normalized in the sense that if you have one single global section, you say that the topological complexity is 0. And in this case, for this vibration, and that's equivalent to the space being contractible. Now, the relation to the model in robotics is that when if you think of X as being the space of configurations of a robot, then the free paths are just the movements of the robot, and the Cartesian product is the space of tasks, namely pairs of initial positions of the robot and a final wanted position of the robot. And then having a section for this is just having a rule assigning to each task an action solving the task. And of course, I don't want to go out the topological category, so I insist that the sections are continuous, and this has an interpretation in terms of robotics. Namely, you want that the section, that small perturbations of your task result in small variations of the action to solve that task. Okay, so well, one of the things that capture one of the reasons that why these ideas capture the attention of topologists is that this number is actually a homotopy type invariant of X. Okay, so here's a quick sketch of what would be the main basic TC tasks. There is, on the one hand, the estimation of this number, and also understanding it in more theoretical ways. What are the general properties? In the estimation side, there is worked ideas given upper bounds for this number that involve essentially you're dealing with a multi-sectional problem, so you can use some form of obstruction theory that's usually really very hard, and that's one of the last resources that one should use. There is also some lower bounds coming from the cohomological viewpoint, and these are actually very computable. Sometimes these two numbers agree, sometimes they don't, and then you have to work more in order to get the right answer, if you can at all. And related to this is also the task of constructing optimal motion planners, namely describing precisely what are the pieces of the base space in which you have to break it into, and the actual local sections. That would be a motion planner. And actually last week I was in a computer science conference, and I gave a talk about this, about how you could implement these ideas to put a computer to work and potentially substitute these hard homotopy computations. But in this talk I want to focus on the property side, the more theoretical the properties of this invariant. Now, one of the things that are motivating this talk is, in particular,
how does this thing behave on products of spaces or after you attach a cell, or for that matter, a cone? And what are these numbers for general families of spaces, of manifolds? Now, TC, of course, is a close relative of the Lusternik-Schneiderman category. Namely, they come from, they are just given by sectional category of suitable vibration. But in a sense, topological complexity is a little bit rich. It came more recently, much more recently, from an input from robotics, whereas category came from understanding the nature and counting, at least, the critical numbers of more functions. Now, here's a way why I say, a way to saying why TC is somehow homotopically richer than category. So suppose this is the vibration defining the topological complexity, but let me restrict it to one of the sections. Let me send an element x into a base point, fixed base point, comma x, and take the induced, the restricted vibration. Of course, the restricted vibration is just paths starting at a base point, which is a contractible space. Now, the sectional category of this, which is the topological complexity, cannot increase when you take a pullbacks, so you get all of immediately this lower bound, namely the sectional category of a point mapping into X is just a Lusternik-Schneiderman category. On the other hand, the sectional category of any vibration is bounded from above by the category of the base space. So one immediately has this, basically for free, these two inequalities. Now, one of the things that I want to point out is that the first one is actually sharp when the space is an H space. This is a result of Lupton and Schroeder. Also, the upper estimate is also sharp when you have simply connected closed symplectic manifolds. That's one of the first results that Farber himself described. But now, about what's the nature of this number, it turns out that this number can be anywhere in between these two bounds. Namely, choose any number c, little c, and take any number little t in between c and 2c. Then there is a polyhedral product whose category is z and whose topological complexity is that t. So you can just say it in advance what you want. And this was proven by Dan Cohen and a student of his, Pruzzi. I think that's the last name. Anyway, but let me, the idea that I want to stress here about why this invariant is somehow homotopically richer comes from understanding Ganea type conjectures for these invariants. So, well, it's well known that the category is satisfies this inequality. The category of a product is bounded from above by the sum of the categories of the factors. Now, in the case when one of the factors is a sphere whose category is then 1, of course, one has this estimate. And on the TC side, one has something similar. But now the topological complexity of a sphere is quite easy to compute, standard. And it turns out to depend on the parity of the dimension of the sphere, on the one hand. So you already have this inequality. And, well, in the case of category, Ganea, at the beginning of the last century, of the previous century, after playing with these things, proposed several questions, and one of them was whether there was a space for which this inequality was not an equality. It actually was a lot of examples were known, many families of manifolds where these two numbers actually agreed. Also, it is true in the rational case, but at the end, by the end of the previous century, Iwase came with an actual counterexample, and this uses very fine homotopy information. Now, the point is that you can now get inspired by those techniques and produce corresponding counterexamples for what would be the TC analog for the Ganea conjecture. And so here is one result. Suppose Y stands for this stunted a projective space. Namely, here is a nice whale picture of this space. It has 4 dimensions where it has a single cell. This is the action of the steam rod algebra. So this pretty much describes the homotopy type of this space. And now take the wedge sum of Y with itself. Then it turns out that the topological complexity of that space is 4, which is the most it can be just by upper estimates. But the topological complexity of that space crossed with a sphere increases only by 1 for even-dimensional spheres, whereas the topological complexity of those even-dimensional spheres is 2. So it didn't go up as one would expect. Okay, now the point is that this is really a byproduct result. This is just something that you can do with the techniques. And the main contribution then is actually the techniques. Okay, so let me say a few words how those ideas began. So it's quite clear that if you take the category of a space after attaching a cell, it can increase only by 1 at most, because you're attaching a cone, and that's contractible. All right, and that would be true for even if you attach a cone. Okay, now you would like to say, well, how can I characterize whether it doesn't go up by that 1? And there is a well-understood obstruction which was first introduced by Whitehead and later on by Bernstein and Hilton, which is a generalization of the Hopf invariant in the case of maps between spheres. And it has the property that that thing, which is a set of homotopy classes, it has indeterminacy, vanishes, namely it contains a null homotopy class, if and only if the thing doesn't go up, it stays bounded by the category of the space without the additional cell. Now, in Iwase's example, this is the moral. This is how it works, without going into details. So suppose you take one of the generators. Well, there are 2 generators. A generator of the homotopy of the 9th homotopy group of P of S3. That's known to be a Z03. Okay. Now take the Hopf map, the very first Hopf map. That's a generator of P3 of S2, which is Z. And let alpha be the composite. Then, well, what would be the classical Hopf invariant of that thing? Well, that's the Hopf invariant of the composition, of course. And in Whitehead's description of the Hopf invariant of a map between spheres, it is given precisely as the obstruction for this map of being a co-H map. Now, in the case of beta, this is not a suspension, but it is a co-H map. So the obstruction for this being a co-H map only depends on this guy, because this is a co-H map. So in other words, it's well understood that the Hopf invariant being 0 for beta means that this equality holds. And of course, the Hopf map has Hopf invariant 1. So that's basically the identity. So this invariant is non-zero. So according to this thing, to this result, if you attach this cell, a 10-dimensional cell to S2 via this map, then you have a non-trivial Hopf invariant, and so the category goes up by 1 with respect to the bottom sphere. That's okay. But then it wasn't noted that when you take this product of this space, 2-cell complex with Sn, well, this is a picture of this space. You have one factor with cells in 0, 2, and 10, another factor with cells in 0 and n. Now you can take the top cell. Here's a structure for what is remaining. This structure is trying to suggest to you that this is obtained by a 2-step cone decomposition. It has a cone decomposition of length 2, namely you have the bottom cell, the product of the zeros, and then these 2 cells, even though they are different dimensions, they can be attached at once. And then the cells corresponding to the darker lines, to the thicker lines, correspond to the next cell, to the next level of cells that can be attached. So the point is that the category of this part is at most 2. And actually, since it contains this axis, and the axis has category 2, it cannot be any lower. So this category is 2. And now you're asking what would be the category of this after attaching this cell. So according to this result, you would need to understand the Hopf invariant of this attaching map. What Iwase did was to show that the Hopf invariant of this new attaching map is only a multiple suspension of the original Hopf invariant of alpha. This alpha has the property that after a suspension does not vanish yet, but the second suspension and after that, it vanishes. So this gives immediately an example where, even though you are attaching a cell, it has a trivial obstruction, and then the category of the thing remains being 2 and doesn't go up. So this is basically the idea. Of course, this is the key point in his argument. So what we need is a way to, well, first of all, define generalized Hopf maps and understand their role in the sectional, understanding sectional category of vibrations. And well, that would be fine, but more importantly is to have effective ways of evaluating these obstructions, of course, if you want to do anything with that. So here's the classical approach to understanding the sectional category of, say, a vibration P from E down to B. The key feature here is the fiber-wise join power of the map P, which I denote that way. So what this space is basically the space of all n simplices with vertices in the fibers. In a common fiber, all the vertices have to be in the same fiber, but the fibers can then vary. So this is just the fiber-wise join construction of this of the original vibration. All right, now what is this good for? Well, it allows us to reduce a multi-sectioning problem to a single sectioning problem. Namely, you have, say, at most, you have at least n+1 local sections. If you have so many sections, n+1 local sections, then you can use, that means that you are covering the base space of that vibration by n+1 open sets, and then you can take a partition of unit and use the corresponding functions as the barycentric coordinates of the original local sections to assemble one global section. So that essentially gives one direction, but the whole procedure is reversible. So the point is that if you want to give upper bounds, well, you can do it by constructing global section for this new vibration. Now, the usual way, or the standard way of doing this, but maybe not the most convenient in general, is that using obstruction theory. Of course, if you have your vibration and you want to construct a global section, then you can try to construct it on a skeleton by skeleton basis. Equivalently, you can decompose your original vibration into a sequence of principal vibrations whose fiber are Eilenberg-MacLane spaces. Namely, you start adding one homotopic group of the fiber one at a time. So this is the classical construction of Postnikov towers. And now dealing with those things is really a very hard thing because, well, there is higher and higher indeterminacy. That means that you have, when you're constructing your partial liftings, sometimes you have to go around and start over again because you will get to a dead end. So that's one thing. The other thing is that the obstructions lie in cohomology groups with coefficients in the homotopic groups of the fiber. Computing homotopic groups of things is just a pain on the neck. So you may want to just try to avoid that. And the other sort of problem here is what n should I start with? If I go all over the place, the procedure, and suspect that I cannot go and control a global section, well, that wouldn't mean that it doesn't exist. Or maybe the n was too low. So it doesn't give me an insight on what n should I start with. So what's the solution? Let's try to modify the obstruction theory. And when I get to this point, I always remember what Sam did in his earlier work, and actually one of the most important works in homotopy theory when he was actually quite young. Namely, instead of using usual Postnikov towers, he developed it together with Mark Mahorwald, a modified version of it. He described what they call the modified Postnikov towers. They are still decomposing into sequence of principal fibrations, but the fibers are now not Eilenberg-MacLane spaces with one single homotopy group of the fiber at a time, but they are product of those. They call them generalized Eilenberg-MacLane spaces. But what was the idea really behind all that? Namely, much of the problem is computing the homotopy groups of the fibers. Now, there is an algorithmic way, unquote, of computing homotopy groups of spaces, namely the Adam spectral sequence, or unstable versions of the Adam spectral sequence. The beginning of this machinery is actually homological algebra, so that's algorithmical. That can be computed. And so what they did was, okay, instead of resolving each homotopy group, complete homotopy group at a time, let's use information at one common level in the Adam spectral sequence. Instead of taking columns in the Adam spectral sequence, take rows, which means taking elements of low Adams filtration. And in some cases, the spectral sequence collapses, and that actually gives you a way not only of computing the beginning, but also computing the K invariants. So, well, that's more or less, I like to think that this is more or less the motivation for this. And the idea is that I want to replace K invariants by Hopf invariants in this procedure. All right. So here's the basic construction. The beginning is really very simple. Suppose you have the fibration P for which you want to understand what the sectional category of that is. And suppose you have any old map phi from X into B and take the pullback diagram. Let me define the relative sectional category of P relative to phi of 5, whatever that is, to be just the sectional category of the pullback. Again, the sectional category doesn't increase after taking pullback, so one has this upper bound. And in the case where the base space you started with is obtained from X by attaching a cone, and this is the corresponding inclusion, then it can be shown very easily that the sectional category does, even though it can increase, it can increase, it doesn't increase by more than 1 with respect to the relative version of it. So the idea then is that you can iterate this. Suppose you have your fibration, and then you describe a cone decomposition of the base space. Namely, you are taking a family of subspaces, and each of them is obtained from the previous one by attaching some cone. Then you can say, okay, at the beginning, obviously you have a 0 sectional category, the relative one. This one can increase at most by 1, this one can increase at most by 2, and so on, and this one can increase at most by k. So, of course, the idea is to decide whether it increases or not. But at any point, this gets rid of the problem of deciding at which stage you should start. Then you just start at 0 and then decide whether it goes up or not, and so on. Also, this gives an effective way of evaluating the sectional category of the whole thing by as long as you can evaluate the partial obstruction. So you're just decomposing a large problem into smaller ones. Now, one key thing here is that you will always have primary indeterminacy. Indeterminacy increases, really increases. That's a problem, but it's always primary. You don't have to go over on the process and start over. Maybe. And maybe the main point here is that this is actually computable, it's accessible in many cases, and this is the whole point of this talk. So here's the general setting. Suppose I have only one piece. I'm analyzing only one piece. So I have a fibration, and the base space is obtained from X by attaching a cone, so you have this co-fiber sequence. And suppose that the relative sectional category of P relative to phi is n. All right, so let me go back to the fiberglass joint construction for P. So I take this thing. I already know that if I restrict this over X, that admits a section. That's the hypothesis. So that means that you have this lifting. And of course, since this composite is that composite which is not homotopic, this map factors through the fiber up to homotopy. All right, so one thing to notice is that if this map is trivial, then this composite will be trivial, so this map would be trivial, and that just means by standard techniques in homotopy theory that this partial lifting can be extended to a lifting of the whole thing. So that suggests that we should take a look at the following definition. Define the Hopf set associated to alpha, and it depends also in the whole thing, to be the set of homotopy classes of these maps as you vary the liftings. Liftings are not necessarily unique, so you really have sort of a indeterminacy. So I'm going to, as I said, I'm going to call this set a Hopf set. The elements are going to be called Hopf invariants. And what I said over here is the fact that this set is trivial, meaning that the null homotopy class belongs to it, if and only if you have a section for this, namely if and only if the sectional category, the absolute sectional category of P, is N. It doesn't go up. It stays on this side. So essentially you have to evaluate. You have to be able to say whether or not a set of homotopy classes contains the null homotopy class or not. This is sort of tautological. It's a very complicated problem, so you really need a way to put your hands on these things. So here's an example. I want to exemplify these ideas into this, what I already mentioned. The fact that the topological complexity of a sphere is either 1 or 2 depending on the parity of the dimension of the sphere. This computation is standard. That was one of the first things that Farber found. This is standard. This is very simple. But I want to give an explanation of this equality in terms of homotopy theory, Hopf invariants in these terms. So I have here the fibration defining this number, the double evaluation map. Now I notice that the base space has a cone decomposition, your obvious cone decomposition of length 2. Let me just start with the wedge of two things and attach. You start, of course, with a point, then you attach a wedge of two spheres of dimension n-1. Take the cone, that's this thing. That's the thing. And then you attach the very top cell. All right, so because this has length 2, this can be at most 2, of course. On the other hand, you can argue that this fibration restricted over here has sectional category exactly 1. That's quite easy. That's explained here. So you have that this fibration has sectional category 1 here, and you want to know whether it has sectional category 2 or 1 on the larger space. So according to the plan, the general setting in the previous slide, what you have to do is take your cone decomposition. You're looking to you're trying to see whether it stays being 1 or 2. So you have to take this fiber-wise joint product, and then of course you have a lifting because here you have TZ being 1, and you have the corresponding map landing into the fiber here. The first thing to note is that it is a standard that this space decomposes as a wedge of spheres. The bottom cell is of dimension 2n-1. So that means that this map is a 2n-1 equivalence. And this is in a larger range of the dimension of this. So this is a unique lifting. There is essentially a unique lifting up to homotopy. There is no indeterminacy in this case. So there is a well understood Hopf invariant, a single Hopf invariant. Well, it's not well understood yet. So I want to say, what is this map? Of course, it goes from S to n-1 to this wedge, but for obvious reason, it lands into the very top cell, and then it's described just by degree of this map. So it is a number. This is a plain number. And in fact, the theorem is that this number is essentially is optimum isomorphism, the classical Hopf invariant of the Whitehead product of the two inclusions on the wedge summons. And it's a standard that this number is either 0 or 2, depending on the parity of n. So if you will believe this, then that says that when n is 0, you have a trivial obstruction, so topological complexity doesn't go up. And when it is even, then it does go up. So what I want to, this is trusting that you can actually compute this thing and say that it is this number. But I want to give two different reasons why this is so. One, by comparison, comparing with other things, and other, an explicit computation, homology computation. All right, so here is the comparison. So here, what I did here is the same here as this. It's the same thing as we have here. We have your cone decomposition of the sphere, of the product of the spheres. This is the fibration that I'm interested in. I have the lifting and the corresponding Hopf invariant. Now I want to understand this map, of course. So I'm going to compare it, and the key map in this picture is this one, going from the Cartesian product into the cone of the diagonal. So let me just make a pause here and describe what that is. So consider this diagram, if you can. I think it's too small. But let's see, here's a plain description. So here I have the diagonal. This in this direction, this is supposed to denote that this is diagonal. Namely, up to homotopy, the diagonal decomposes as the coproduct map inside the product, the Cartesian product. All right, so okay, I want to understand the cofiber of that thing. So this map is going to be that map. But let me just continue. So before going all the way to here, from here to here, let's analyze this square first. So this is the sum, the co-product, and this is the map, which is the identity and changes the orientation on the other summand. So the composition is trivial. If you look at a homology, this is a short exact sequence, so that means this is a cofibration. In other words, this is a homotopy push-out diagram, this one. Good. Now, let me just include into the wedge into the Cartesian product. Up to here I have this square and this map, and also this map. So take, by definition, the push-out diagram here. Let me take this space to be the push-out diagram. Since the two squares are push-outs, the whole rectangle is a push-out, and that, since you have here a contractible space, that means that this is the cone on this composite, which is, as I said, the diagonal. So I already described the cone on the diagonal. All right, but now notice that this inclusion is just inclusion of the two bottom cells on the Cartesian product, and here's the attaching map. By definition, this Whitehead product is just the attaching map of the top cell, for the top cell of this space. So in other words, this is a cofibration. So you have also here a homotopy push-out diagram. And now you have two homotopy push-out diagrams, so the composition is also a homotopy push-out diagram, and you have a contractible space here, so that means that this space is just a cofiber now of the whole composite, but the composite is obviously this Whitehead product, namely the square. Up to a sign, this is the Whitehead square of the identity of Sn. All right, so now let me use this square, which is right in here. This is the map Q, the inclusion, these two maps packed together, and inclusion. Now, notice that these squares is obviously commutative, and now I have this, at least this part, mapping down into this, the base of that thing, that thing. But now, what about this part? Well, what you have to notice is that the double evaluation is essentially the inclusion of the diagonal. And if you take the inclusion of the diagonal and take the cofiber, I should make a drawing here. Can we have lights? No. Thanks. So the point here is that I have the double evaluation map. And what I said is that this has the homotopy type of the diagonal. Namely, if you have a free path, you can just shrink it through the middle point. That gives you this homotopy, and what you're doing then is just sending to the diagonal. And what I describe here is the cone on that thing. So here you have a null homotopic map. So these factors through this space. But what is this map? This is, of course, I already mentioned this is the base paths on the cone. So that means that you have a way of mapping, and this is the single, in these terms, this is the evaluation only at the free end of the path, of the base path. So this means that you have a way of mapping this vibration into this vibration. And what these maps are just the functorial resulting maps in the J1 functor after taking the fiber-wise construction. So you have these maps, and the whole diagram fits together. And it's quite easy to see that what you get here then, of course, if you're taking this, the sectional category of this map, what you're measuring is the category of this space, because this is contractible. So what you get here is precisely the situation for understanding via Hopf invariants the category of that thing. Namely, you know that the category, the relative category here is 1, and you want to understand whether it goes up or not. So essentially, that tells you that this resulting map is the obstruction, what I described at the very beginning in the work of Bernstein and Hilton. Whoop. Lose myself. Oh, yeah, there it is. But now the whole diagram is commutative, so look in particular to this square. One key point is to observe that this map is an equivalence in a large range. So this map, what I'm saying is that this map is an equivalence. And so since this is the identity, essentially this homotopy class goes under an isomorphism into this other homotopy Hopf invariant. So via this isomorphism, this guy and this guy can be identified, and this is what I said here. So it's a bit too much of a homotopy, but yeah, okay, sorry. All right, so, but again, I have to depend on the fact that you can compute this Hopf invariant in classical terms. This is well understood, but yet let me insist on that this is computable. You can actually describe a way to compute it, and I'm going to put the main goal now is to give a general setting for computing these objects, not only in this particular case. Okay, so what's the idea? The idea is, it turns out that notice that we have this diagram. I was, let's see, let me organize my ideas. I want to understand, so I suppose that I understand the category of X, namely the sectional category of this evaluation map. That's okay. And now notice that I have this diagram. Namely, I can take the Cartesian square of this vibration with itself here. The fiber is just the product of the fibers. Notice that this is just the base paths on the Cartesian product. And now I have here the vibration defined in TC. And notice that there is a nice map from this vibration into this vibration. Namely, it takes a path in here, which is a path of a pair of paths going up from one common point, into just go through this thing that way and then that way. So this is just the multiplication. On the fibers, this is just the twisted multiplication in a group, in a Hopf space. Okay, so the idea is, if you can understand Hopf invariants for this vibration, then you can just push them via this map to understand, hopefully, Hopf invariants for this other vibration, which is the one that I'm interested in. All right, so in more general terms, I want to understand Hopf invariants for a product of vibrations. And there's a very nice result for that. And I need to define one shuffle map. And this is actually one very, very standard, well, it's not a standard construction. It's based on the standard triangulation of a product of simplices. So suppose you take delta n cross delta n. These are topological realizations of this simplicial, abstract simplicial stuff. So this is you can triangulate this. There's a canonical way of doing it in the category of order abstract simplicial complexes, for instance. It is a union of simplices, all of which are copies of this guy, and is indexed by m, n, m shuffles, namely n plus n permutations. And here's a very nice toy example of what is going on. What we learn, what do the homotopy invariants of homology, you have to consider the prism operator. So here you have delta 2 cross delta 1. This is delta 2, cross it with delta 1. So here's this prism. Now here's the three tetrahedra that are dividing this prism. And it depends on shuffling cards. You have a deck of 2 cards and a deck of 1 card now, very small one. So for each shuffle of these cards, I'm going to describe as an ordering of these vertices going from here to here. For instance, in the very first case, suppose I have this shuffling. Whenever I have, since I have the 2 cards, I have 2 cards coming from the left disk first. So that means that I'm going to start here, and I'm going to increase this number by 1. That's for this card. And for the other one, I'm going to increase again the same side by 1. And then there will come in this card, which means that you have to increase this guy. If you look at what is happening, I'm describing the nodes that are supposed to be in red here, this, and this. So I have 1 shuffle, 2 shuffles, and then go up. So that describes this little tetrahedron in red. And so on. Here's the shuffling, which is left, right, left. So that means that you increase left, then you increase right, and you increase left. Or that means that you go from here, or horizontal, vertical, and horizontal, and then you consider the middle tetrahedron inside this prism. And similarly for the other one. So here is a very nice description. So let me define this for this permutation. I want to define this ordering of the vertices of this in this decomposition. I want to stress that I've defined these numbers, these sequences of vertices, and I also have these canonical homeomorphisms between the 3 simplices dividing the prism. And then this allows me to finally define what I need. Namely, there is a shuffle map going from the nth iterated self-join of a space A times Jm of B, another space, which shuffles barycentric coordinates and vertices. And it goes to the n plus m iterated joint construction of the product. And what it does is the following. Suppose you have a tetrahedron here. It has vertices A, those are supposed to be vertices in A. It has barycentric coordinates, and similar here. Notice that T, S are elements in this guy. So this is a union of these simplices that I described. You look at where it lands, and then define this way. Depending on this ordering, you're shuffling here vertices and shuffling barycentric coordinates. So essentially, this describes for you very, maybe a little bit, it might look a bit complicated map, but it is geometrically very simple map. So simple that you can actually do computations with it. And before that, this is not quite yet the map that I want. Namely, now you can do the following thing. Take this space, and let me include it on this factor is going to be the identity And here I have the inclusion of the cone. Then, from the cone, I just map this cone into the next joint product of A with itself, namely taking one of the faces going through a base point to there. That's basically this map. And then shuffle. But now I included this, I increased this number by 1, and I'm shuffling. I can do the same construction on the other axis, and one verifies, because definitions are quite explicit, that this diagram commutes, and so it defines a map from the union of two things. But that's nothing but the join. It's cone times a space, union space times the cone on the other guy. That's just the join, and you have here some, by now, probably mysterious map, but I told you it's quite accessible. It's very geometrical. This is a shuffling of vertices and barycentric coordinates. Now, I already said that you have a very good control on what this map is in homology. Notice that both spaces are n+n+1 iterated self-suspensions. Iterated suspensions. So, and this is the homology of that. That's homology of that. And you can actually describe this map as a sum of some components. It is well understood. Let me not go into detail about that. It's understood. Here's an example. Suppose A is the loops on SP, V is the loops on another copy of SP. Now you take the shuffling and this nice map that I want to use when comparing E1 times E1 to E2, from cat cross cat to TC. Now the point is that the bottom cells of these are these guys, and the bottom cell of that is that guy. And if you're able to compute homology, then you can decide what the degree of this map is in the bottom cell. And it turns out to be given as the sum of the number of positive shuffles of n+1, n+1, plus -1 to the p times the number of negative such things. Now, this is this map and how it relates to this auxiliary map. But the main result is this one. Namely, you want to be able to compare Hopf invariants for a product and produce a Hopf invariant where you can put your hands on for the product, if you know from the factors. So here is the result. Suppose you have two fibrations. I is either 1 or 2. You have two fibrations, fibers, total spaces, and base spaces. The base space in each case has a cone decomposition. This guy is obtained from this by attaching some cone. These spaces doesn't have to be spheres. You're not necessarily attaching cells, just attaching cones. Now suppose that this fibration in the relative case is, you know it, is Ni. And it has Hi as a Hopf invariant, as I already described. Now notice that the Cartesian product has a top cell, well, top cone. And that's obtained by taking this product and mapping from the join of the two things. Here, essentially what I'm saying, lights on please, las luces. What I'm doing here is that dn plus m, of course, is dn cross dm. And this is, of course, the cone on Sn plus m minus 1. And this is, of course, the cone on Sn times the cone on Sm. So essentially, product of two cones is the cone on the join. So this is what I'm doing here. So you have this top cone, not top gun, top cone here. And the conclusion, finally, is that, okay, then you know that this vibration relative to here has sectional category at most n plus 1, sorry, n1 plus n2, the sum of the two relative sectional categories plus 1. And not only that, the critical thing is that you actually have a Hopf invariant. And that's given by the join of the previous Hopf invariants together with the shuffling. In other words, a Hopf invariant for a product is the shuffle of the Hopf invariants of the factors. This is what this is asserting. Now let me use it in this example that I already showed you. I was trying to tell you why this is so in homotopy terms. So we came with, it depends on having this computation. And of course, this is the Hopf invariant that you have to understand. It goes from S2n minus 1 to essentially the bottom cell, which splits. So this is a number that you have to understand. But let me compute it. And here's what you do. Recall this map comparing the Cartesian product of the cats with the TC, the vibration defining those things. And of course, I have to understand the very first Hopf invariant for the sphere. That's easy. The corresponding Hopf invariant is just inclusion on the bottom cell here. This is the plane inclusion. Now I take the product of these two things, and what this theorem tells me is that the resulting Hopf invariant is given by the join of these Hopf invariants, and then you have to shuffle. And then I can just push them through this map, this twisted multiplication on the fibers. But now, notice that the Hopf, then recall that this was unique because this is highly connective. So this is the same as this composite because there is only one Hopf invariant up to homotopy. So what that is, this invariant then is just this composite. And that composite you can just associate this way. Of course, the join of the bottom cells is just the bottom cells of the resulting thing. And that's essentially what you're saying is, okay, so what's the degree of this map on the bottom sphere? So this is just the degree included into the range space, the target space. And the formula that I already gave, I mentioned as an example, tells you that this is so. This is just a homological computation. So let me finish, I'm almost done, with saying, okay, this is just playing with these ideas in this baby toy example, but essentially the same methods allow you to to understand topological complexity of a two-cell complex. If you try to do it by conventional methods, it's going to be very difficult. It's not known. It's very complicated. So here's this allows you to give a method to try to approach this problem. So suppose then X is then the cone is a two-cell complex with attaching map alpha from SQ to SP, very general setting. So here's a description of the Cartesian product. Here you have a factor. Recall that X has cells in dimension 0, the base point, then has a cell in dimension P, and then has a cell in dimension Q plus 1, and this is this axis, essentially. And this is the other axis, and this is the product cell decomposition. But now, notice that these two cells, of course, are the same dimension, so they're basically part of the one skeleton. But these three cells, this one and this one are the same dimension, but this is not the same dimension. But anyway, the three can be attached all together to here, obviously, and so on. So you have a fourth, a cone decomposition of length fourth. For instance, here you see one axis. Here's the other axis. This is the Cartesian product. For instance, this guy is just the product of X across the bottom cell, or the same for this thing, etc. So we have 4 possible obstructions, and so the alternatives for these numbers, they go from 0 to 4, and of course we have to say what are the corresponding obstructions. Here's the result. First of all, the easy case is when the Hopf invariant of the attaching map of X is trivial. In that case, we already know that the category doesn't go up, it's the same as the bottom cell, and in that case, it's also very elementary to prove that topological complexity is actually 2. So the interesting thing is when the Hopf invariant of the attaching map is non-zero. So in particular, the category of that thing does go up by 1, and then we have to decide whether the topological complexity is either 2, 3, or 4. Now the fact that you already have this lower bound coming from here tells you essentially that the very first 2 obstructions are non-trivial. And in particular, the relative TZ up to here of this triangle is 2. But there are the top 2, last 2 obstructions. And here's a description of them. Now I have to be gentle with myself. I'm going to be assuming that the attaching map is in the metastable range. If it is in the stable range, it is a suspension, and the Hopf invariant is 0, so that's in the easy case. So suppose now you're in the next range of interesting homotopy theory, what is called the metastable range. Namely, I'm assuming that you have these inequalities. Then the techniques that I just described tell you that the third Hopf invariant is essentially a multiple of the original Hopf invariant of the attaching map of X. And also you can compute, and notice that there is no indeterminacy. This Hopf invariant is a singleton. And if the Hopf invariant, this third obstruction is non-zero, then the fourth one doesn't have indeterminacy, and you can actually explicitly describe it. In particular, you have an if and only if condition for TC being the top one. You have a sufficient condition for being 3. There are some observations in which, just by numerical reasons, some of these are well behaved, and that gives you an answer of 3. So let me finish just by mentioning 3 general ideas. So here I'm saying that if the very top obstruction is non-zero, then you can decide what value is. Now, what if this obstruction is 0? Then it depends on the previous obstruction, and that would be then 3. But suppose that before going to this obstruction, before going to the fourth obstruction, the third one is 0. So what if it is 0? Then topological complexity from here to here stays being 2, and then going from here to here is either can stay being 2 or increase being 3. But there is, in that case, I cannot describe the Hopf invariant essentially because it has indeterminacy. That's pretty much of the problem. So one thing is that this approach is dramatically lacking a well handling of indeterminacies. And this is pretty much what you can actually handle in the modified Postnikov-Tagore approach of Sam and Mark. And so the idea is, okay, can you still modify even further this theory so that to be able not only to understand the obstructions but the indeterminacy. That's pretty much of the problem. And the other thing that I want to mention is that the application that I mentioned to the TC Ganea conjecture is just one single example of this whole algorithm, these whole ideas being put into work. But I just gave an example of a space when you cross it with even dimensional spheres that does not go up two levels, but it could go up 2. I described that it goes only 1, but there are more examples that would be interesting to have, where the topological complexity of the product stays being the same as the one of the factors, or what happens if you take odd dimensional spheres. So, well, thank you very much.
Questions?
So this gives you the TC of 2 cell complexes.
Metastable range. Only in the metastable range, and there is one case which is not decided. You have 4 obstructions. The first two being I can tell you that are non-trivial. If the third one is 0, then the next one does not comes in a lower degree, and in that degree has possible determinacy. I cannot say what that is. But if the third one is non-zero, then I can tell you what would be the answer, because I know explicitly a description of the fourth last obstruction. But there is one point missing description.
Where are more cells, or a cell attached to a wedge?
Good question.
No questions? So let's thank the speaker again.